Welcome to week 2 of our course. This is lecture 7. The topic is local rings and localizations. Okay, so this is week 2. So the topic of lecture 7 is local rings and localizations. So this will be a lot of recollection of facts from ring theory. We say that a commutative ring R is local we call it a local ring if it has a unique maximal ideal. Okay, so some recollection of facts from ring theory. This is a process called localization that allows us to construct local rings. So the setup is, so we work with a simplified setup. Let A be a domain with fraction field K. And take a multiplicatively closed set. In A. By which we mean, so we say that the set S is multiplicatively closed. Our assumption is that 1 belongs to S, and we assume that 0 does not belong to S. And if you have two elements, say S1 and S2 in this set, then their product also belongs to S. Okay. And you've already seen an example of a multiplicatively closed set. If you have a prime ideal, let's call it P, then the set I'll denote it as P, which is all the elements of A that are not in P. So this is a multiplicatively closed set. In A. Okay, and for any multiplicatively closed set, you can form the localization for any multiplicatively closed set S in A, one can form the localization which we denote S inverse A. And in this simplified setup, when A is a domain, we can think of it as a subset of the fraction field. So I just think of all the elements of the form A over S, the numerator and denominator. So this fraction is in the fraction field of A, with the property that the numerator belongs to A and the denominator belongs to S. Okay, so this localization turns out to be a ring. Containing A, since by assumption 1 belongs to S, so A sits inside S inverse A, and that sits inside the fraction field of A, which we call K. And note that since A is a domain, one example of a prime ideal is a zero ideal. And in this case, the set SP is just all the elements of A that's not 0. And then it's not hard to see that this localization is in fact equal to the fraction field of K. And in general, if P is a prime ideal, then this localization SP inverse of A, this is a local ring, which means it has a unique maximal ideal. And what is the maximal ideal? It's in fact given by the localization of P. So SP inverse of P, which is again all expressions of the form x over S that's in this ring inside the fraction field with the property that the numerator belongs to the prime ideal P and the denominator belongs to this multiplicatively closed set SP. Okay, and in general you have this new ring S inverse A. What are the ideals of S inverse A? Again, I'm just recalling some facts. So every ideal of the localization is of the form, you try to localize the ideal itself, so it's all expressions, all fractions x over S inside the ring with the numerator belonging to the ideal and the denominator belonging to the multiplicatively closed set. And just a word of caution, in general there could be multiple choices of I. So that when you localize you get the corresponding ideal in the localization. So there might be multiple choices of I, and an example of this sort is, you just take the integers, the usual integers, and you take the multiplicatively closed set given by the prime ideal 2, so z minus 2z. The fraction field of A of the integers is just the rational numbers. So the localized ring in this case is just all the fractions x over S with the property that x belongs to z and the denominator S belongs to z minus 2z. Okay, and maybe just a small observation, z minus 2z, you're from all the integers you're removing the even integers, so what you're left with are odd integers. Now you can try to localize 2z, so you get all fractions with the property that the numerator x is even and the denominator is odd. Okay, you could also maybe play the same game with say 6z, where the numerator is a multiple of 6, and remember the 6 is 2 times 3 and 3 is an odd number, and the denominator are all the odd numbers, and it's a standard exercise to check that in this, under this localization, the ideal generated by 2 and the ideal generated by 6 are in fact equal. Okay, so show that they are equal in this localization of z with S being z minus 2z. Okay, so the point I'm trying to make is that in general, if you give me an ideal in the localization, there are multiple choices of ideals in A that give you the corresponding ideal in the localization. However, if we simply restrict ourselves to prime ideals, there's a nice one-to-one correspondence. So for every prime ideal Q of S inverse A, there exists a unique prime ideal little q in the ring with the property that the intersection of Q with S as the empty set and once you take the localization of Q, little q, you get back the prime ideal big Q of the localization. Okay, so some more facts. If you take a prime ideal in your ring or your domain A, then when you take the quotient, since P is a prime ideal, the quotient is a domain, and now associated to this P and A, we can look at the localization. I'll denote the localization as A subscript P to be the localization with respect to SP inverse, where this SP is A minus P. Now I mentioned earlier that this is a local ring with maximal ideal given by the localization of the prime ideal P. And since you have a ring and a maximal ideal, if you take the quotient, then this is the field, and you can ask how is it related to A or P. So this is naturally isomorphic to the fraction field of A over P. The localization AP, when you mod out by its maximal ideal, you get a field, and that's naturally isomorphic to the fraction field of A over P. Okay, and so just to summarize, in general, you have a domain sitting inside K, and then you have this multiplicatively closed set S, and it could be possible that this K is sitting inside some other field. So K is a field, L is a field, A is a domain, and S is a multiplicatively closed set. And maybe there is inside L, maybe you have another A module. So this is a setup that we've seen. It could be inside K, or it could be inside some larger field. And upon localizing, so if M is an A module, then S inverse M is a module over S inverse A. And we can view S inverse M in the simplified setup. Since M sits inside L, you can think of it as fractions again inside L, where the numerator belongs to M and the denominator belongs to S. Okay, so time for a lemma. Lemma 15. So suppose you have an inclusion of domains inside some field L, and suppose S is a multiplicatively closed set in A. If this inclusion turns out to be an integral extension, if A inside B is an integral extension, then so is the extension given by S inverse A into S inverse B. Okay, so let's do a quick proof of this. So every element of this localization S inverse B is of the form B over S, where the numerator belongs to B and the denominator belongs to S. And since every element of the ring B is integral over A, so since little b, which belongs to big B, is integral over the ring A, it satisfies a monic polynomial over A. So So you have b to the m plus am minus 1, b to the m minus 1, so on, plus a1b plus a naught equals 0, with these coefficients am minus 1, a1, a naught belonging to a. Now I'm interested in looking at this fraction b over s. So I'm just going to divide throughout by an appropriate power of s. So dividing throughout by s to the m, we get, so I take this monic equation and then I divide throughout by s to the m. So if I look at b to the m over s to the m, I have b over s the whole raised to m, and then I have b over s the whole raised to m minus 1, and what's left is am minus 1 divided by s. And in general, the general ith term of this monic equation looks like b over s the whole raised to I, and what's left is a m minus I divided by s to the I, and that goes on up to b over s plus a1 s to the m minus 1 plus a naught s to the m minus 1 equals 0. And now what we have is that with each with a coefficient here a m minus I over s to the I, this in fact the numerator belongs to a and the denominator is s times s times s times s I times, but s is a multiplicatively closed set, so the denominator belongs to s. So this fraction belongs to the localization, since the numerator belongs to a and the denominator s to the I is just multiplying s I times, and that belongs to the multiplicatively closed set. Okay. So what we get is a monic equation satisfied by b over s, where the coefficients are in the localization s inverse a, and so thus b over s is integral over s inverse a, and this completes the proof. So thus the localization s inverse b is integral over the localization s inverse a, and this completes the proof of the lemma. Okay. One more lemma, which is a slight upgrade to the previous lemma. So lemma 16. So suppose we let O denote the integral closure of a domain, say A, inside a field L, and suppose you take a multiplicatively closed set inside A, then the localization of the integral closure S inverse O is in fact the integral closure of S inverse A. Okay. So proof, so let's call B the integral closure of S inverse A in L, and since O is the integral closure of A, we have that the inclusion A inside O is integral, and this is almost by definition of what O is. By the previous lemma, which was lemma 15, we have that S inverse A inside S inverse O is integral. So every element of the localization S inverse O is in fact integral over S inverse A, and all these localizations are taking place inside L. So what we have is that S inverse O must lie inside the integral closure of S inverse A, the integral closure of S inverse A in L. So this localization S inverse O must lie inside B. Okay. Now let's try to prove the reverse inclusion. So conversely, suppose you take an element little b in B, and suppose it satisfies a monic equation of the following form. Plus Cm minus 1 b to the m minus 1, so on C1b plus C naught equals 0, where so B is the integral closure of S inverse A, so all these coefficients Ci should belong to localization S inverse A, and so we can write the Ci as a fraction Ai over Si, with the numerator belonging to A and the denominator belonging to S. Okay, and now I'll just make this choice. So I have all these denominators S0, S1 up to Sm minus 1. So let me call little s this product Sm minus 1, so on and so forth, S1, S0. So I'm just multiplying out all the denominators given by these coefficients, and since I'm multiplying elements in this multiplicatively closed set S, this product should also lie in S, since each little si belongs to S and the set itself is multiplicatively closed. And so in particular, if I take S over Si, this ratio has to belong to A. Okay. So now I have this equation out here. If I write each Ci in terms of A and S, Ai and Si, I get b to the m plus Am minus 1, Sm minus 1, b to the m minus 1, so on and so forth, Ai, Si, b to the I, plus so on and so forth, A1, S1b plus A naught, S naught equals 0. And now if I multiply throughout by S to the m, what do you get? I get that S times B. Now again I play the same trick of collecting coefficients. I have S to the m times B to the m, and I can collect it and write this as SB raised to m. Now I collect m minus 1 copies of S and m minus 1 copies of B, so I have SB to the m minus 1, and what's remaining is Am minus 1 S divided by Sm minus 1. Now if I just keep playing the same game, I have Ai Sb the whole raised to I, S raised to m minus I over Si. Okay, so on and so forth. A1 S raised to m minus 1 divided by S1 plus A naught S to the m equals 0. Okay, and now look at each of the coefficients. Of this equation. That's of the form AI s raised to m minus I over si. And so if you just write this as AI s raised to m minus I minus 1 times s divided by si. We've just seen earlier that the ratio s over si belongs to A. So you're multiplying three things that are in A, so this product should also lie in A. Okay. And what that means is we get a monic equation over A that's satisfied by SB. Okay. Since O is the integral closure of A in L, what this means is that this element S times B must belong to O. And so if we write SB as some x which belongs to O, this just means that B equals x over S. And so this has to belong to the localization with respect to S of O. And so every arbitrary element of B lies in this localization. So we prove the reverse inclusion that B sits inside S inverse O. So we got in both inclusions, and so we have that B equals S inverse O, and this completes the proof of the lemma. Thank you.